In this lesson, we're going to take a look at the domain and range of graphs. So what is the domain? Well, recently we've been looking at the idea of intervals in mathematics and how to list intervals. The domain is the interval of all the x values for a function or a relation. The range is the interval of all the y values for a function or a relation. So we were doing intervals basically just on one of the two axes. Now we're going to do it for both at the same time. And we're going to do that by just looking at how does the graph behave along the x-axis and how does the graph behave along the y-axis. Now we're actually going to start with one that's a little bit different than what we've seen in class recently. And what we have here is what's called a discrete graph. Now, what is discrete data? Discrete data is data where the points aren't connected, and that could be because you're dealing with things that you count that can't have decimal values. So this is actually one of the easiest graphs to deal with, because when you're dealing with domain and range for a discrete function, all you do is list all of the possible values for x for the domain and all of the possible y values for the graph as well for the range. So if we look here, there's an x value at -4, there's a dot, right? So if we wanted the coordinate of that dot, we would say it was -4 and 5. But we're only interested in the x values for the domain. So there is a point at -4. There is a point at -3. There is a point at -2. So we just want to list all of those points. If you look at the way I wrote the domain here, so there's a couple of things you need to know. We usually write the letter D to represent domain, and we use these curly weird brackets here to enclose all of the points. And we had seen these as set notation in a previous lesson. So that's usually the brackets that we use to represent the domain and the range. And as you can see, all I did was list all of the x values for my points. -4, -3, -2, -1, 0, 1, 2, 3, 4, and 5. There are dots on all of those x values. For the range, we're going to do the same thing. Now, we usually want to do it by finding the minimum point first and going up towards the maximum point. So even though the first point for y, normally we read the graph from left to right, and it actually doesn't matter. You could do that if you want. So the first y value here is 5. I actually went and found the minimum value, which is -4, and then started listing all of the y values for each one of those points. So -4, there's a point, -3, there's a point, -2, there's a point, -1, there's a point, etc., etc. So I just listed all of those. If you wanted to do it 5, 4, 3, 2, 1 in that order, that is fine as well. But usually we like to list them from the smallest value to the biggest value. And that is what we do for a discrete graph. So any type of graph where you only have points like that, you would just list what all of those points are. So what happens if you don't have a discrete graph? Well, what I would recommend when you're looking at a graph like this is, let's talk about the x values first. What is the smallest x value and what is the biggest x value? So what are the minimum values and the maximum values for the x? Well, if we look on the graph right here, this is the smallest x value, and that's at -3. So I know that my minimum x value is going to be -3. Now, if I travel along the x-axis, I have to look at the graph's shape here, and we've got these arrows at the end of the graph. And that means that the graph continues forever in both of those directions. So that means like at x equals 5,000, there is going to be a y value above there because the graph is continuing forever. So what we usually say when a graph continues forever is that its maximum value is infinity. It doesn't stop. And as you see here, I listed the minimum value as -3. So this graph exists everywhere to the right of -3, in other words. And it includes all of the decimal values. So we don't have discrete values here. We have a line connecting all the points, and that means all the points between integers are there as well. So there's actually a point here at negative 1.6. Okay, there's an actual value above that x value on the graph. So if we look at how we write the domain, this is what it's going to look like. Again, D to represent domain. We use our little curly brackets, and this goes back to our interval notation that we were talking about in the last few days. We say x is an element of the real numbers because that includes all of the decimal values. And then we say that x is greater than or equal to negative 3. And the greater than or equal to a number is going to also include the maximum value of 1,000 because you just keep getting bigger and bigger past negative 3. So you don't actually have, as some of our intervals had, two numbers, a minimum and a maximum. We just state if the graph is bigger than a number in this case, or in other cases, whether it's smaller than a number. And that includes the infinity. Okay, so since the graph is greater than negative 3 forever, including negative 3, because it's a solid dot right there. I'll just erase that line so you can see that. Okay, there's no open circle as we've seen recently. There's a solid dot right there. So it includes negative 3. Now if we talk about the y direction, does the graph have a smallest y value? Well, if we look at the arrow, that means that the graph is going continuously downwards. Therefore, there is no minimum y. It just continues forever all the way up to negative infinity. And the same thing up here, because the arrow continues to go up, there is going to be a point. If I go all the way up to like positive 100 on my y-axis and I go over, at some point I'm going to be touching my graph. So there is going to be a point at positive 100, at positive 1,000, at positive 1 million, at negative 1 million. There's going to be a point on my graph because of those arrows. So to show that, this is actually relatively easy. We're going to say the minimum value is negative infinity. The maximum value is negative infinity, which basically includes every possible point that exists on the y-axis. We just state that the range, sorry about that, the range is y is an element of R. We don't use this notation for greater than, smaller than, because there is no greater than, smaller than. Every value exists. So we just say y is an element of R. Let's go to the next picture. So this type of graph, which is pretty much brand new for grade 11, is what we call a piecewise graph. A piecewise graph is a graph that has a break in it, but it's all considered to be one graph. So when we talk about this style of graph, we need to say what is the domain of the entire thing, and that's the x-axis values, and what is the range of the entire thing, which is the y-axis values. So once again, let's talk about the minimum and maximum x values here. So what is the smallest x value? Well, the smallest x value is at negative 5, but it doesn't include negative 5 because it's an open circle. So I'm just going to write open to remind me that that negative 5 technically isn't included. We're getting really, really close to negative 5, so negative 4.999999999, but we're not getting exactly to negative 5. The maximum x value is, let's say that's, if this is 5 and that's 10, that's like about 11. So let's say that the maximum value is around 11. I have to estimate here because I'm not exactly sure. It's ending somewhere in the middle of that square. I now have my minimum and my maximum is actually a solid point. So it's not an open circle, so it's a solid point. Now there is an open circle here, okay? But if I asked you at 5, is there a solid y value somewhere? Even though there's an open circle here, there is actually a closed circle right above it. So there is a closed value y above the 5. And that means there is a solid point there. If there hadn't been, that would be another issue that I'm maybe going to talk about in a minute. But because there's a solid point there, I can say that there's a coordinate at 5, and let's say that's around 6, okay? So at 5, 6, there's an actual solid point, even though there's an open circle here. So we're not going to worry about that open circle above the 5. What is my domain? Well, first of all, do I have decimals included? And the answer is yes, because there are solid lines connecting those things. So because I have solid lines connecting those things, I have to say that x is an element of the real numbers. We have to start there. There are decimals involved. And now let's talk about our minimum and maximums. So this is one of those intervals where we have x in the middle of these symbols here. Those symbols, the way we read this is x is greater than the number that's here, and x is smaller than the number that's on the right. So what number is x greater than? X is greater than -5, which is my minimum x value. And then I have to decide, do I put an equal bar or equal sign underneath this small greater than symbol, or do I not? And that's why I wrote that -5 is an open circle. We do not put the equal sign here because it doesn't include -5. It gets really close to it, but it doesn't include it. For the maximum value, we've already written that that's 11. I'm going to put the maximum here, and then I have to decide, do I put the little equal sign under there? And the answer is yes, because that is a solid dot right there. So I'm going to put the little equal sign under there, close my curly bracket, and that is my domain. For the range, we have a little bit of an interesting scenario here. If I'm looking at this graph on the y-axis, there are actually only 2 y values in existence here. That would be a y value that's around 2.5, and that's at around a height of 6. Okay, so again, I'm estimating it's approximately 2.5, like 2.49. I'm just going to say it's 2.5 as a height, and this height is approximately 6. There are only 2 values for the y. There is no line connecting vertically here. There's no other lines above. Those are the only 2 y values. And that makes the y values discrete. Because there are only 2 heights, and they're completely separated by empty space, we are going to say that my range, I don't state y is an element of R because it's not an element of R. It's only 2 numbers. I'm going to just list 2.5 as one of the heights and 6 as the other one, and then close my curly bracket. So piecewise graphs often have some part of them that is discrete and some part of them that isn't. Let's look at this one. This is an interesting shape to a graph. You've probably never seen this before. This is actually a 1 over x graph, and we'll talk about that later on. But let's talk about our minimum and maximum x values here. So if I'm going along the x-axis, I have an arrow here and I have an arrow here. That means the graph never stops in both of the 2 directions. Now there is something weird that's happening down this dotted line in the middle here at x equals 2. The graph skims along at x equals 2. It goes upwards at x equals 2 and it goes downwards at x equals 2. But these 2 arrows here and here are basically stating that the line, or the curve I should say, the blue curve, never ever touches the dotted line. It just skims along the dotted line. And that means there's like a break in the graph here. Now that break is called a vertical asymptote. Big word here. Anytime you have a situation where a graph skims along a part of the x and y axis and doesn't actually touch that spot, it's called an asymptote, and that is actually a break in the graph. So we have to talk about that break. Okay, now let's talk about the minimum and maximum first. The minimum is going to be negative infinity because the graph continues to the left forever. The maximum is going to be positive infinity because the graph continues to the right forever. But there's a break at x equals 2. And the way we state breaks is we say that x can't be equal to that number. There's no graph at x equals 2 because it just skims along and never touches it. So there's actually no coordinate at x equals 2. So we state that x can't be equal to 2. So how do I write that in my domain? Well, otherwise, besides the x can't equal 2, the graph exists everywhere. So we're just going to write x as an element of R to show that the graph exists everywhere. And then we're going to put a comma, and we're going to write x can't equal 2 and close my domain. That's stating that the graph exists everywhere except for at x equals 2. Now for my y values, we're going to see that things are very similar. Along the y-axis, what is my minimum? Well, the arrow down here, as I was mentioning, it skims along this dotted line at 2, but it never stops going downwards. So my minimum is negative infinity because of that arrow, and my maximum is positive infinity because of that arrow. But you're going to notice that along the y-axis, there's another break in the graph. As I'm going up the graph, and I get to this dotted line right here at about 1, the graph skims along that horizontal line and never touches it. So is there a y coordinate at 1? The answer is no. There are no y values at 1. So again, there's another break, and we're going to say, whoops, I almost wrote x there, that the graph doesn't exist at y equals 1. So we say y can't equal to 1. And then we write our range. It's going to look very similar to our domain. We say y is an element of R, and y can't be equal to 1. Let's look at another example. Now this is actually a graph that you are used to seeing. This is just a straight line graph. A y equals mx plus b graph. Where does this graph exist? Well, look at these arrows. The graph is continuing to the left forever, continuing to the right forever. That means x has a minimum value of negative infinity and a maximum value of positive infinity. So my domain for a straight line graph is just x is an element of the real numbers. For the y values, the minimum as well, because of the arrows, is negative infinity, and the maximum is positive infinity because it goes forever up and down. That means the range is just y is an element of the real numbers. I had talked about an open circle scenario that I wanted to discuss, so let's do that right now. What if we had the exact same style of graph? So I'm just going to put an x and y axis here. But this time, instead of just a line, we have a line with a break in it. I'm going to try to line these up a little bit more. And I'm going to put an open circle right here. And we're going to say that open circle is at a height of 2 and a horizontal distance of 1. Okay? So it is possible to have graphs that have we call them a hole or an open circle in the middle of the graph like this. And in this case, we do have to talk about it because as I move along the x-axis, when I get to 1, there is no y-coordinate above it this time. It's an open circle. That means there's no coordinate there. I have to state that in my domain. Same thing if I go along the y-axis. When I get to 2, there's also an open circle right next to it. There is no y value at that open circle. We have to somehow state that in our domain. So all we do in a case like that, I'm not going to write out the whole minimum and maximum thing because we've already seen for a linear line that its x is an element of R normally. It exists forever in the x-axis. But we would then say that x can't be equal to 1. Similar to what we did with an asymptote, we just say that that point doesn't exist on the x-axis. For the range, we would do a similar thing. We would say y is an element of R, and we would say y can't be equal to 2 because there is no point at y equals 2. There's an open hole there. It is impossible to show every possibility, but this is going to give you a pretty good start to see how you would talk about these graphs, and we can do more of them in class. Now, I would also like to talk about what happens with equations and very specific types of equations. How do we talk about the domain and range? Now, you already know some equations. You know y equals mx plus b is a straight line, and the domain is going to be x is an element of R, and y is an element of R for the range, because a straight line exists everywhere. You've also seen parabolas. Now, a parabola can either have a smallest point and continue on forever in the y direction upwards, or it can have a highest point and continue on in the y direction forever downwards. So your domain, your x values, continue forever because these arrows mean that the graph continues in that direction and continues in that direction horizontally. So my domain for a parabola is always x is an element of R. But the range, depending on whether the parabola opens up or opens down, in the first case here, oops, that's supposed to be a y, we would say y is an element of R, but we would then say y is greater than or equal to a number if it's going upwards. And here we would say for the range, y is an element of R, but y is smaller than or equal to a number because it's going downwards from that point. So you've already seen those two. You've seen their shapes, I mean. So you've seen parabolas and you've seen straight lines. But what happens if you have an equation that looks like this? So this is called a rational equation because you have an x on the bottom of the fraction. Rationals just means fractions. It's another word for fraction. But as soon as you have an x on the bottom of the fraction, we have a problem. We have a problem because the denominator can never be 0. And if you have an x on the bottom of the fraction, we have to state a restriction. What value can x not have? Because if x had that value, it would make the denominator equal to 0. And that restriction is x can't be equal to 4 in this case. Because if x was equal to 4, the denominator would be 0. At x equals 4. Okay? So we have to state a restriction, and when we state a restriction, that restriction is included in the domain and range. So for these graphs, they exist everywhere except for where the restriction is. Oops. I'm having a little bit of trouble with some of my symbols here. The range, however, goes forever. So anytime you have an x on the bottom of a fraction like this, you have to state the restriction. The restriction is what x value would make the equation equal to 0, and therefore say that those two values are not acceptable for the x values. And that is where I'm going to stop the lesson here. Hopefully that's explained to you a little bit more. How do we write the domain and range for at least a few examples? I can't go through every graph. We will do some more in class, but that should be enough to get you started. Have a great day.